Welcome to Astrum Space and Galaxy, your gateway to the wonders of the universe.
Picture yourself standing on a peaceful hill, observing the sky explode into a rainbow of color as the sun peaks above. The horizon, it's a daily spectacle that many of us take for granted, the warm hues of orange, red, and pink splashing across the sky, yet this lovely sunrise is merely the last chapter in the light's long journey. If we trace the path of these photons from the endpoint in the retina, the back of your eye, through the Earth's atmosphere across the 150 million kilometer void, separating our planet from its host star, and finally through the varied and tumultuous layers of said star, we find the cause of the TAs, of the warmth on your cheek and the hues brush strokes, across sky the core of the sun, a nuclear fire that has been burning for 4.5 billion years. Conceive in a cosmic cradle from the remains of older star, the radiating sphere of burning plasma that which fills our skies, the result of intricate forces that have unfolded over millennia. So let's take a trip back in time, following the beginnings of the sun, investigating its complex layers and charting ingredients which form its very fabric. What lies at the back of the blinding veil of light and time it takes to know how sun came to be formed. We need to take a step back before our solar system itself came into being some 4.6 billion years ago. Then, in a pretty calm area of the Milky Way galaxy, a huge gas and dust cloud called a giant molecular cloud moved quietly across space. This was no typical cloud. It was gigantic, perhaps hundreds of light years across, and with a mass equal to millions of suns inside. This cloud were the dispersed remains of ancient stars that had long since burned out their nuclear fuel and detonated as supernova, throwing their enriched contents into the cosmos's stellar consisted of a blend of elements such as hydrogen and helium, the raw materials of stars, and heavier elements such as carbon, oxygen, nitrogen, and iron. The existence of these elements made this molecular cloud rich soil for the creation of new stars and planetary systems. But such a gigantic cloud needs a catalyst to start the collapse by cascade Wicker salts. In stellar birth, researchers think that catalyst would have been a shock front from a nearby supernova explosion that compresses portions off cloud, causing it to fragment and collapse into regions of higher density. This collapse marked the beginning of the Polar Nebula, the dense region within the molecular cloud that would eventually give birth to our solar system. Some scientists have even proposed a name for this hypothetical explained star, Coatleque, named for the Aztec goddess of earth and fertility. Kate represent the cycle of death and rebirth, in which in this instance a demise of one star may witness new ones emerging. As the gravitational collapse of the giant molecular cloud went on, it didn't lead to a single huge object, but instead broken up into many heavy clumps. This breaking up happens because of an effect called Jean's instability. After the British scientist Sir James Jean's length of the Jean is a key distance within a cloud, where gravity's forces are balanced with the natural internal gas pressure that keeps the cloud propped up. When a defined section of the cloud exceeds the Jean's length, it will collapse in on itself. Different regions within the molecular cloud exceed this Jean's length at different times due to variations in density and temperature. As these regions become gravitationally unstable, they collapse indefinitely to create several protostellar cores. As compared to a single massive Bototheath, protostellar core was the first stag in our sun's life that was apparently starlickising itself into a tighter and tighter sphere by the ever-clenching fist of its own gravity. The core is enveloped by infalling gas and dust. As additional material piles up, the core grows denser and hotter, paving the way forth. Next step of star formation, the protostar. After a protostellar core is dense and hot enough, it transforms into a protostellar's inner region has warmed up to the extent that it starts radiating light and heat from the energy released due to gravitational contraction, but its interior has not yet attained the temperature as necessary to cause nuclear fusion to take place in the core. As the protostar keeps on adding material and enlarged in mass, the pressure and temperature within its core shot up our sun, evolving this embryonic phase of contraction and warming over millions of years before it slowly accumulated its core temperature to around 10 million DC. at which time hydrogen nuclei start to fuse into helium. And with that, the sun was born at this stage. The innate angular momentum of the surrounding material that shrouds the infant star generates rotation. A cloud of this size will always have some slight rotation. Nothing in the universe is still in conservation. Angular momentum instructs that the cloud has to spin faster and faster as it compresses down into smaller space, like a figure skater spinning faster as they fold in their arms along the axis of rotation. Some of the material is going so fast that it remains in orbit, but up higher and down below the momentum is not enough to counteract. The protostar hungry grasp and falls helplessly into its mouth, and so the cloud becomes flat into a disk, a protoplanetaritus. This disk is a cosmic lottery as it cools and coalesces. Planets, moons, asteroids, and comets will be relenting, formed, and dissolved. Some matter will lose its momentum and tumble into sun, while surrounding matter will continue to become one of the numerous bodies that constitute our solar system today, with its new power to fuse hydrogen atoms to helium. The sun could funnel Protus energy to counteract the forces of gravity. I tried to compress it even more. The energy pouring out of the fusion processes produced an outward radiation pressure that counteracted the inward gravitational pull of Thegas, enabling the young star to reach a stable condition referred to as hydrostatic equilibrium. In this state, the star ceases to contract due to its own gravity, and it settles into a stable stage of its existence, referred to as the main sequence. This balancing act between inward pressure forcing outward and gravity squeezing in is the axis which determines each stage of the sun and all stars. We saw it during the first collapse, and here as it settles into a stable main sequence star, and it will be a pendulum that ultimately swings towards its dramatic death. For now, let's deconstruct the process of nuclear fusion and how it's able to sustain an object is huge, as the sun's stable and consistent for billions of years. In order to see how nuclear fusion works in the sun, we must study extreme conditions found inside. Its core temperatures are approximately 15 million C and pressures over 250 billion times that of the atmosphere of the Earth. In this scorching cauldron, hydrogen atoms lose their electron secreting, a plasma made up of 3 protons and electrons. Under these intense conditions, these protons that normally repel each other with their common positive electric charges are crowded into very close proximity. The force that tends to keep them apart is the Coulomb force, an electrostatic repulsion. The positively charged particles, it's the same force that holds back as you attempt to push the some ends of a bar magnet together, overcoming this force. Force is the biggest challenge for nuclear fusion to take place, despite the huge kinetic energy of protons in the core of the sun. Most collisions are even not energetic enough to overcome the Coulomb barrier. Under standard circumstances, protons require tremendous energy to reach close enough so the strong nuclear force may hold them together. This barrier is such that physicists at the time, roughly around the early 1920s, with a classical conception, the particles are interacting
with one
another, decide that fusion does not happen at the temperatures and pressures of the sun's core. In order to fix the puzzle, we had to have a scientific model which can account for many of the seemingly impossible things we see happening in the universe. Quantum mechanics. The 1920s revolution in quantum mechanics brought with it the idea of particle existing, both as particles and as waves. One such phenomenon is quantum tunneling, where particles shave some probability of passing through a barrier even when they do not possess the classical energy had to surmount it in the core of the sun. Quantum tunneling provides a means for a few protons able to get past the Coulomb barrier without needing to climb over it in the traditional manner. Although these protons lack sufficient kinetic energy to overcome the electrostatic repulsion itself, quantum mechanics provides them an opportunity to show up on the other side of the barrier in order to conceptualize this process. Look at a diagram of the Coulomb barrier. In the diagram you will notice a large energy barrier depicting the repulsive electrostatic force between 2 protons at different distances. The energy required to scale over this barrier is depicted as a peak. The calculations of a classical physicist would demand the sun to have temperatures high in the billions of DC. thousands and thousands times greater than the core of the sun, to overcome this barrier, but quantum mechanics permits the probability. Wave of a proton to tunnel through this barrier, to show up on the other side without ever crossing the top. This tunneling effect is what is fusion possible in stars such as the sun, in spite of what appears to be the impossible Kohn barrier. After a proton has penetrated the Kohn barrier, it is close enough to another proton, fourth strong nuclear force, to dominate the strong nuclear force, which is much stronger than Theculum force, acts only at extremely short ranges on the order of femtometers. Where 1 fomer equals 10 to the 15 m, about the size of a single proton, the strong nuclear force holds the protons together, but this is only the first step in a chain of nuclear events called the proton-proton chain. The proton-proton chain reaction is the major fusion route in the Sun and other similarly sized stars, responsible for producing about 99% of the Sun's energy. It begins with 2 protons that wander freely, coming together to create a heavy hydrogen isotope and the emission of a neutrino and a positron. This step is rare but critical because it permits the fusion process to proceed. The deuterium then quickly combines with another proton to create helium-3, releasing a high-energy photon. A gamma ray and the last step to helium-free nuclei collide and combine to produce helium for releasing 2 protons and a large quantity of energy in the form of radiation. While the proton-proton chain is the most prevalent fusion process in the Sun, there is another route work, especially in stars hotter and more massive than the Sun. This route is called the CN cycle, abbreviated as carbon, nitrogen, oxygen. In this cycle, carbon, nitrogen, and oxygen nuclei serve as catalysts to merge protons into helium. The CNO cycle is more efficient at high temperature and contributes only a small fraction of our Sun's energy output. The energy generated in these fusion reactions is due to a small portion of mass being converted into energy, as defined by Einstein's well-known equation EALMC2. In the fusion process, the mass of the resulting helium for nucleus is slightly less than the total mass of the original 4 protons. This missing mass is not lost, but instead transferred into energy that travels outward from the Sun. Each second, the Sun takes approximately 3 million tons of its own mass and converts it into energy. That's right. The Sun is constantly losing mass topless. This, in perspective, is equivalent to the mass of roughly 3 million cars being converted into pure energy every second. This is the energy that actually powers the Sun and gives the light and heat that comes to Earth. But prior to the photons flooding out of these reactions, reaching the Earth and the rest of the solar system and beyond, they first have to escape the 700,000 km turbulent solar interior that sits above them. To fully understand the complexity of the Sun and its stratified layers, let's trace a solitary photon, a particle of light, from its origin within a proton-proton reaction up to the surface. This process is far from simple, in fact, that it will take thousands, if not hundreds of thousands of years for this photon to finish its journey, traveling through a number of distinct layers off-Sun with each one of their own individual properties and behaviors, which we've already discovered. Our photon's journey begins in the core, an area that covers approximately 25% of the radius of the Sun, but contains close to half of its mass overall. And as we've also learned, that core is extremely dense. At approximately 160 g per cubic cm, it is more than 20 times denser than iron topet. That in context, if your phone was constructed of that density material, it would weigh as much as a sledgehammer of heavy duty for our photon. This implies that the environment is so densely packed with particles it cannot go far before being absorbed by a neighboring particle. Of course, not long later, that particle will pack the photon bags and send it out into the of the core for another particle to capture and release in some other random direction. It's similar to attempting to move through a packed crowd, where with each few steps you hit someone and need to change direction. This constant absorption and re-emission is what makes the core chaotic nature, so that the trip for a photon is a random walk rather than a straight trajectory outward. This random trajectory of photons is similar to Brownian motion, in which particles that are suspended in a fluid travel in a fitful manner. Two collisions with the smaller, rapidly moving molecules, and there is no bias for which way. A photon might fly back out of a particle that had just absorbed it. In theory, a photon may get as far as the surface of before no chance sends it flying back towards the core to add to the complication, as photons are constantly absorbed and re-emitted. The energy continuously reduces from gamma-rays to X-rays and finally to visible light. As they travel towards the sun's out layers comprehending the processes happening within the sun's core has been a daunting task for astronomers. The core is interreliabs, obscured by the sun's outer layers, meaning we can't directly see it by any form of light. Rather, scientists have used clever ways to deduce the dynamics of the roaring inferno beneath. One of the principal methods is helioseismology, the study of observation of waves rippling the surface of the sun. Just like seismologists examine earthquakes to understand Earth's interior, helioseismologists observe the vibrations on the sun's surface produced by sound waves. Propagating through its interior, these sound waves are affected by the temperature, density, and constitution of the layer, enabling physicists to build models of what is going on deep in solar. Neutrinos, illusive subatic particles that I've discussed in an earlier video, are also emitted in the fusion process within the core of the sun. Neutrinos interact so weakly with matter that they can travel straight out of the sun in just 2 seconds, hardly aware of the tangle there. Photon counterparts are caught up in 4-decade solar neutrino detectors on Earth measured fewer neutrinos than predicted by theoretical models, leading to what was known as the solar neutrino problem. It wasn't until scientists found that neutrinos altered their characteristics or flavors during their travels to our planet that the enigma had been solved, affirming both our comprehension of particle physics and the nuclear reactions. In the heart of the sun, next photon enters the radiative zone that stretches from the boundary of the core to roughly 70% of the sun's radius. Here, temperatures slowly decline from 15 million to roughly 2 million to see the matter's density. Also declines, going from roughly the density of gold in the depths of the zone to below water. Near the surface, the energy transportation that Rein's method remains this phonetic process of photons skittering through the layer with their energy in average to the surface, and with the decrease in density of the plasma as we travel outward. Our photon has a bit more room to wiggleable to make longer leaps between interactions. Butivin, out here away from the center, the material of the sun is still so dense that even a few centim could stop as much light as several hundred meters of water. We can envision such detailed models of the interior of the sun because of models such as the Standard Solar Model or SSM. It is a mathematical frac based on the principles of hydrostatic equilibrium, energy conservation, and radiative veteranfer, essentially using our understanding of how materials and fluids behave here in our laboratories on Earth to infer the properties of a place out of our reach. The SSM model synergies pass between particles and its complex equations describing how photons are transported via the dense plasma. This enables us to compute how see-through the solar material is to radiation at various temperatures and densities, and from there we can determine where the radiative zone finishes and the subsequent layer starts. This is one of my favorite aspects of mathematics. It enables us to investigate the worlds that we can never go tonally, nearly like the way quantum tunneling lets protons tunnel through the colon barrier and give rise to photons that we're currently tracking as our phot. As it moves towards the top of the radiative zone, it moves into the tachocline, a narrow transitional layer where the radiative zone crosses over to the next layer, the convective zone, the tacho. Cline is a setting of radical contrast where the relative uniformity of the radiative zone encounters the boiling boo and convective zone. The bizarre conditions in this incredibly thin layer probably has a major part in the solar dynamo, responsible for creating the sun's magnetic field. The cline is intended to twist and amplify the magnetic field and shaping the sunspots and solar flares that characterize the star surface hipping. Past the thin tachocline, our photon reaches the convective zone, extending out from around 70% of the sun's radius to just below the surface that is visible. The photosphere, the temperature sheave fallen below 2 million C. Now the plasma of the sun isn't dense enough to transfer energy effectively. Radiation instead, the plasma becomes unstable and starts moving in huge convection currents. Similar to boiling water in a pot, hot plasma rises towards the surface line. Big cells named granules. These granules with diameters of thousands of kilometers surge aboard under their power of buoyancy at rates of hundreds of m. Second, similar to a beach ball that you force beneath the water, surging to the top as it squirms out from beneath you. The force needed to push this amount of matter against the gravity of the sun is an incredible picture. The force of 10 billion hurricanes, and you'd be only beginning to approach. The energy required this process of convection transfers energy much more effectively than the radiative zone, forming turbulent rolling waves off plasma that churn strongly. I have described these convection cells and the beautiful hypnoticatons they form on the sun's surface in a lot of detail in this earlier video. This is a drastic shift in the means of transporting energy, though. Photons continue to exchange with particles. The main process of transferring energy in the convective zone is no longer the indiscriminate absorption and re-emission between particles, but now it is the flow of hot plasma rising and cooler plasma sinking. This convection motion transports the energy outward more effectively. In the radiative zone, when it reaches the end of the convective zone, the photon is transported to the photosphere. The visible surface temperatures of the sun now have cooled to approximately 500, and the plasma has become thin enough for photons to escape without being continuously reabsorbed. It is from this narrow, approximately 500 thick layer that the light that we observe from the sun is emitted. Above them, there's only the sun's corona, which is itself an interesting environment, but only a billionth density of the photosphere, and thus not much of a barrier. To our photonet is amazing with an object such as the sun that most of us call a ball of gas, can have a sharp boundary, but the photosphere is where our photon finally gets away, moving at the speed of light and starting its journey across the endlessness of space. Our neutrino pal, who was created at the same time, it's long out of the Milky Way by now since settling into its stable main sequence phase. Nuclear fusion has altered the strength of the sun's layers, gradually increasing brightness over billions of years. This is because the fusion process inevitably leads to changes in the composition, density, and temperature of the sun's core, which in turn affects the overall behavior and the future of our star as hydrogen fuses into helium. Hydrogen gradually in the core, and helium ash begins to build up, unlike hydrogen, which readily undergoes fusion. At the sun's existing core temperatures, helium takes much higher temperatures to diffuse. The helium abundance makes the core denser. Helium nuclei are heavier than hydrogen nuclei, and since the more helium that accumulates in the core, the greater the overall density is at the same time, because the helium is not fusing and producing energy, it does not add to the outward radiation pressure that opposes sun's gigantic gravitational pull. The consequence is that gravity will start to take over, letting the core to shrink even further. To avoid collapse under its own gravity, the sun must increase its core temperature. As helium builds up, the hotter core turns up the dial on hydrogen fusion, because nuclear fusion rates are extreme elicitive to changes in temperature. This increase in fusion releases more energy, which results in a brighter star and temporarily restores the balance between gravity and radiation pressure. Through this process, the energy output of the sun has increased by approximately 30% throughout its lifetime, and this trend will last for billions of years. As long as hydrogen fusion reigns in the core and the radiative zone, the layers have become hotter and more opaque. The increasing temperature of thicker means more energetic photons are produced, which are more prone to interacting with the surrounding plasma and pinballing around. As a result, this zone has become less efficient, radiating energy outward, trapping photons for longer before they can continue their escape. The convective zone has also expanded slightly over time due to the increased energy production. As the sun continues to burn through its hydrogen fuel over the course of the next 5 billion years, its core will ultimately be left with too much inert helium that can no longer support fusion under its own pressure. When this occurs, the sun will grow into a red giant, suddenly expending and engulfing the inner planets like Mercury and Venus, and perhaps the Earth. During this stage, the core will shrink and become hotter until it burns in a helium flash, initiating the fusion of helium into heavier elements such as carbon and oxygen, once more swinging the pendulum between the relentless gravitational pounding and the opposing forces of energy from Thecke. This process will build new layers and cause the sun to swell even farther before expelling its outer layers to Croatia. Ghostly remnant, a planetary nebula, the Korathat, will cool and fade into a white dwarf, a dense Earth-sized ember of a one raging fire. This process from a stable star to a red giant, and then finally to a white dwarfus. An amazing and intricate process with a lot of interesting details, which we will no doubt dig through in a next video.